Well, we're approaching the end of this module of Apache Spark. There will be at least one further module on Spark where we'll be covering, at the very least, how to work with the Spark SQL or Spark SQL API. Now, this is a newer API. It's quite a bit richer than the core API that we've been working with on this module. The core API, though, is still very rich and worthwhile, so I hope you've got a lot out of this course. But I have been putting off talking about not just performance, but also some of the inner workings of Spark. And I have been deliberately ignoring some things that I don't think you should be ignoring if you're planning to be a serious user of Apache Spark. Of course, you don't need to know everything that's going on inside Spark, but I believe that having a good handle on the underlying model of Spark gives you a much better chance of writing good Spark jobs. So that's what we're going to be doing in this chapter. Now, I seem to have throughout this course been constantly saying, oh, we'll talk about that in the last chapter on performance. So for that reason, we do have quite a lot of topics to talk about in this chapter. But I'll try to keep it all one single chapter so it's all in one place. And the plan for this session is we're going to look at, first of all, the difference between transformations and actions, which I think we've probably touched on through the course, but it's definitely worth really nailing that down and making it sure that we're clear on what the difference between those two things are. We'll then go on to have a look in detail at the DAG, or the execution plan, and we're going to use once again the web UI that we used back in the chapter on Amazon Elastic MapReduce. We're going to return to that console and we're going to really drill into the details that we're seeing in there. We'll then return to looking at transformations, and we'll talk in detail about the difference between a narrow and a wide transformation. And another way of putting it is we're going to look at what shuffles are and what the stages are that you might have noticed appearing on the console when we're running our programs. We'll have a look at what's happening with partitioning, and I'll talk in particular about one possible problem you might have in real life, which is called a key skew. And I'll also talk about the group by key transformation, which we have done at least once at some point on the course. And I hinted very strongly that there's some problems with group by key, and it's not really performance problems, but it's more just an operational problem with group by key. It's very easy to get out of memory exceptions in your cluster if you're working with group by key. The general advice would be to avoid group by key because you can always do things in a different way, and I'll show you an example of that. And we'll also look at caching and persistence, which sounds like a big scary topic, but actually if you understand transformations and actions, and you can read the DAG, then you will find the concept of caching and persisting quite natural. It's basically going to be a single line of code. Well, we've returned here back to the program that we wrote in the sort of first part of the course, where we were doing the keyword ranking. We were reading in this input text file, which is a big subtitle file, and we're generating a set of keywords ranked by their popularity. Now, I talked in the introduction chapter about the fact that on each of these lines of code, when we're sort of thinking in terms of, let's take this one for example, we're taking an RDD and then we're going to filter that RDD and we're going to end up with a new RDD. And you might have in your head a mental model of a great big set of data being the RDD, and for each line of code we're modifying that RDD. Well, I had to say this in the introduction chapter because I didn't want anyone to be misled, but at a runtime that's absolutely not what is happening. We're not building RDDs on each of these steps. In fact, what we're building is an execution plan. Only when we get to an operation where Spark actually has to do a calculation to provide a result does anything really happen. Now, in this program, in fact, the only point where Spark needs to do any calculations is on the line here where we're doing the take. Now the reason that it has to do something at this point is we are asking for a Java result. Notice the left hand side is this is a regular list rather than an RDD. So it turns out that it's only on this line of code that Sparc has to commit to doing its calculations. Every single previous line of code has merely been building the execution plan. Now for that reason, Sparc makes a differentiation between its operations. The operation here, the final operation, the take, is called an action. Actions are going to make calculations happen, and they're generally going to result in some regular Java objects as a result. So you can think of the actions as being, get me the results. The previous operations, where we've been building what I've been calling new RDDs, actually there's no new RDD being built here. What we're doing is adding a new step to the execution plan, and Sparc calls these transformations. So you really do need to understand the difference between a transformation and an action. Now it might not be obvious immediately why the fact that there's a difference between transformations and actions is relevant, but as we go through this chapter you'll see that it really is relevant, and we will need to keep in mind whether we're doing a transformation or an action. But before we see the impact of this, I'd just like to give you a quick demo really. So I'm going to use the debugger, which I don't use very often, but I can do that with a double click on the left hand kind of column here next to the line number. So I've put a breakpoint on line 28, and I'm going to do a run as debug the main program. I'll assume you're familiar with the debugger, so I won't go on about the debugger. But we've hit the breakpoint now, so we'll switch to the debug perspective. We're now on this line of code here. We haven't yet executed line 28. Now, up until now on this course, I would have been commenting on this code by saying, on this line, we read in the text file, input.txt. Well, can I be really clear and precise now? We are not loading in that text file on this line of code. We are telling Sparc to include in its execution plan the loading of this text file. And the key thing about that is that means this text file will only be read in when it needs to run the execution plan, and that means all the way down here on line 48. Now if I do a step over, I felt that that line was a little bit slow, but can you see in the logging, I'll do a clear on the console, nothing happened there. So where you've been seeing the progress of the jobs and the little animated bar, nothing happened. And actually, as we step over each of these transformations, we're not seeing anything happen in the console. Now, I'm not going to do it here, but if you want to, you could drill into the structure of these RDD objects and you'll see they don't contain any data. We have read no data in at this point. I'm kind of halfway through the script now. No data has been read in. We're merely building that execution plan. Let's keep stepping over. So now I'm not doing edits at this point. So let's take this one. This is just interesting words where we're doing a map to pair. Now, I don't know how long that operation's going to take when it actually executes, but I imagine it's a significant time. And yet when I click this step over, bang, it's taking milliseconds. It's not doing anything heavy. So I keep stepping over. Now actually that reduced to key was a little bit sluggish, but I imagine it's having to do complicated things with the execution plan. It's not working on the data. So I hope I've got that clear, and as we get closer to now, when I stepped over sort by key there, something did happen on the console. Now sort by key is a transformation, so once again, at the risk of boring you, no data has been read in at this point, no calculations were performed there, but something happened on the output. and I'll talk about why that was the case in a short while. But we are now at the action, and if I step over this, now that was the point that the calculations happened. And if I click on the results here in the debugger, the results are going to be a normal Java object. So at that point, Sparc had to do its calculations. That's the first thing to get across, and it can be difficult to remember which of these operations are transformations and which of them are actions. And my best advice here is to use the Sparc documentation. Look for the link to RDD Programming Guide, and there's a link here to transformations, there's one there for actions, and you have here a list of at least the common transformations. So we know now that map, filter, flat map, and distinct, quite a few of those operations we've been doing on the course are all transformations. And we often say these are lazily executed, meaning that these jobs only have to be done, going a little further down, when we reach an action. So common actions are collect, count, first. I don't think we used first, but it's very similar to just doing a take of one, and things such as saving to a text file. So all of these operations will result in the execution plan becoming an execution. So I hope that's understandable, and really that concept is going to be relevant to every single one of these performance aspects that we're going to look at through the rest of the chapter. Now, very much the difficult thing about Sparc is it almost feels like magic what it's doing under the hood. It is incredibly complicated, Sparc, and it can be very difficult to reason about what's happening at runtime. Now, even after working with Sparc for quite a long time, I still find myself, even with relatively simple programs, I still find myself scratching my head and thinking, why did that happen? And why has this performed slowly when I expected that to be quick? So rather than just looking at the program and trying to guess at what's happening, I strongly recommend you get used to looking at the web user interface to get a full view of that execution plan. It's otherwise known as the DAG, which I mentioned in the introduction, stands for Directed Acyclic Graph. It's a bit of jargon from computer science that just means a graph, really, that doesn't have any loops inside it. Well, we did see this very briefly in the chapter on elastic MapReduce, but I reckon it would be good if we could look at that web user interface on our programs when we're running locally. So how can we do that? Well, you saw that on Elastic MapReduce we could look at the history server, which was running on localhost :18080. And the history server will gather together all of the previous jobs that you've already run. Now, this history server is actually supplied by a script which was running on our Elastic MapReduce server. And it's just that was pre-configured by Amazon, so we didn't have to start that script. You can go and download Apache Sparc, and you'll get as part of that distribution a script that you can run, which will run a local web server, and will give you access to that history server. Now, we could do that. I just kind of feel we're getting towards the end of the course, and I don't want to be getting you to install software at this stage. Do investigate that option if you want, but I have a little bit of a hack, which isn't very elegant, I must admit, but it does at least work for basic testing that we're doing here. Now, it turns out that when your program is running, Sparc will start a web server on port 4040 that you can visit, and that will show you the progress of the current executing job. So that's going to be 4040, but we have the same problem that you're only going to get access to that while the job is running, or at least while your Java program is running. So what I will commonly do, and I will warn you, this is a hack, at the bottom of the script, just before we do the sc.close, I'm just going to hold the console. I'm going to create a scanner object from java.util. Don't know if you're familiar with that, but that allows you to read from the console. So we create a new scanner and pass into the constructor an instance of system.in. And that allows us to call scanner dot, and actually be careful, you've got to make sure you've imported this. There's a lot of scanners here. It's the java.util scanner that you're looking for. Standard built-in Java. And then you could call scanner.nextLine. And that will just make the console wait for a text input. And that means we can visit the web UI. Now the downside of doing this is it's very easy then to forget to terminate this program. And you'll notice you've done that when you get a warning when you run the next program and it says I cannot bind to port 4040. So it's a minor downside of doing this, but it's a quick and dirty hack, but it does at least work. So let's run our word count again. Not with the debugger this time, just a normal regular run. And there it's run through. We've got the results, but can you see there the red button is still illuminated. This program's still running and it's actually waiting for me to enter something and hit return. So I'm not going to hit return, but back to the browser. Localhost 4040 gives us a very similar web page to the history web page that we saw when running on Elastic MapReduce. Now there are some things on here that I can't yet explain because they are a little bit complicated, but what we have here is a list of completed jobs. Now a job represents any action that you've performed in your script. Now I say roughly because actually we've only performed one action on our script, as we know, and that was the take. However, and it is just a little bit of a quirk this, and it's difficult for me to explain. To be honest, I've never fully understood it either, but it's due to the internal implementation of sort by key will generate a job. We know sort by key is not an action, it's just a transformation, but it does show up as a job on the Spark console. I don't want to get too hung up on that just now. I might go in a bit more detail about that later, but for now what I want to show you is let's follow the link to the sort by key job. And what we can see now for the first time is the execution plan, as I've been calling it, or as Spark calls it, the DAG. And this is what we've been building up in our code. Each of these transformations is added to the DAG. And I know at first it looks quite scary, but I think once you understand what these stages are, then really all you're seeing is the transformations being carried out one after the other. So let's try to understand what a stage is all about. And a stage is related to a shuffle. So we'll now go on to look at the difference between narrow and wide transformations. Let's run through a simple example to illustrate, and I will actually code this up as well so we can see the resulting execution plans over on real Spark. But imagine we have a text file. This is terabytes from some kind of server, and it's the logging that we saw before. So we have a logging level followed by a colon followed by a date and time. Now on the execution plan, we're going to call the text file method, which adds a node into the execution plan, meaning that when we get to an action, Spark will have to load this file into memory. Well, of course, it doesn't really. What it will do is it will tell the worker nodes to load fragments of the text file into memory. And we're going to end up with a series of partitions, which I know I introduced that in the opening chapter. Just to remind you, a partition is a chunk of data. Now imagine that on our deployment we're going to have two worker nodes, just like we did when we ran Elastic MapReduce. Well, thinking about it, for a terabyte file we probably need a lot more than two worker nodes because of course we need to fit each partition into RAM, but I don't have space on the caption, so assume that two worker nodes is sufficient for this example. And we're going to typically see multiple partitions on each of the nodes. Now that's one example of where I just waved my hands around in the early chapter, and I now want to be specific about why are we seeing multiple partitions? Why doesn't it just have one partition per node, for example? Or to put that another way, how is Spark determining this partitioning? And the answer is it depends on the input source for the RDD. But when you're working with a text file like this, then it's a simple case of Spark will chunk the data. I think we saw this in the Elastic MapReduce chapter. I loaded that big 2 GB file and you saw that the partitions were on Elastic MapReduce, they were 64 megabytes each. So there's nothing complicated going on here other than Spark is just arbitrarily saying, okay, we'll have each partition containing some number of megabytes of the data. The number of megabytes isn't that important and it actually varies depending on what kind of file system you're using. We saw though that it's 64 megabytes when you're using Amazon S3. So that's how we obtained the initial partitions. Now if we'd not loaded in the data from the text file, I can't really think of how that could be the case in this particular example, but my point is, if this RDD had been seeded by a data source other than a text file, it would have simply used the hashes of these strings. Remember, they're just simple strings. It would have calculated the hash code of each of the strings, and then it would have used a modulus of that hash code to, if you like, randomly spread the strings between the different partitions. And that's what I mean by it depends on the input source. So you can see then we've got our strings now scattered sort of randomly across the partitions, and the randomness is just we've taken chunks of the data. But now we're going to go on and we're going to do a transformation. So one of the easy transformations is a filter. Let's say we're only interested in the warnings for this example, so we're going to filter out and we're going to only include the lines that start with the string warn. So you know how this works by now. The Lambda expression is going to be distributed to the individual nodes, actually distributed to each of the partitions. I haven't quite got that across on the slide here, but the point is this function is sent to each of these partitions where it will become a task. So the block of code executing against the partition is called a task. So with this simplified example, we're going to end up with 6 tasks. And those tasks will execute and we're going to end up with our transformed RDDs. So one of the partitions is now empty because there were no warnings and the other partitions have been modified accordingly. Now I hope you can see that all of this could be done totally in parallel and this function could be applied to each partition in turn. Now Spark implemented that transformation without having to move any data around. It didn't have to change the partitions in any way at all. So for that reason, this type of transformation is called a narrow transformation. Let's have a look at another transformation. If we go back to our original input RDD, back to the 6 partitions, and I've got my errors and fatals back in place. We've very commonly on this course done a map to pair transformation. So the input data is a kind of almost a useless string, just a single string. So we've seen on the course it's very useful to split it out into key value pairs. So this would be the resulting RDD. I've not bothered showing the Lambda function for this. It's that business of taking the string and splitting it and extracting the 0th element and the first element. The caption doesn't get this across brilliantly, but I'm denoting there with the round brackets and the warn, comma, and then a date that this is a key and this is a value in a pair RDD. And you know the purpose for doing that. We can do rich operations on the keys such as grouping and sorting that we'll look at that in a minute. But the important thing is this is also a narrow transformation. There's going to be no need for Spark to move the data around in any way to make this happen. Each input partition will simply become an output partition. So it's a narrow transformation. But the reason I wanted to show you this is just to show that when you have one of these narrow transformations, you're going to end up with the situation where the keys are scattered across the partitions. We have an error here, an error here, an error here, and an error here. So that's another narrow transformation. So now that we've got this key value RDD, let's have a look at another transformation we can apply to it. You'll remember, we only did this briefly on the course, but there's a transformation called group by key. And that's going to create a new pair RDD where for each key we have a list In this case, it will be of all of the dates that that logging level occurred. Now, the only way Spark can implement this is it's got to, for example, gather together all of the fatals. So to gather together all of the fatals, it's going to have to move data around from one partition to another. And most significantly, because of course the partitions are spread across multiple physical nodes, that's going to involve network traffic. And not just network traffic, in fact, it's going to have to convert these values, which, okay, for us they're strings, but it could be any Java object, remember. It's going to have to convert those objects into binary so that it can transfer across the network. In other words, it has to serialize all of the data before moving it across the nodes. Now that, I hope you can just feel intuitively, is a very painful operation. It's going to be an expensive operation, and for that reason these transformations have a special name, and that name is a wide transformation. Now I've not finished the caption yet because my animation here is still containing exactly the same information, and that's because I kind of wanted to illustrate this by saying, well, I've got to rework this caption now, and to rework the caption I've got to move the data around. I've got to get all the fatals in the same place, so I'll copy this line here and maybe move it to this partition. So I'll paste that into there. And there's an error here. Let's move all of the errors across to this partition. I'm being a little bit silly here by showing you how painful my work is. I've got to do all of this changing of the caption. Well, I'm illustrating there that Spark has to do that work as well. It is going to be pretty painful. To avoid boring you, I think I'll finish this captioning off camera. Cool, and that was really hard work. I had to shuffle all of these strings around to get them so that they're all clumped together. And as you probably know by now, Spark does indeed call this process shuffling. So a shuffle is triggered by any of the wide transformations, and it is always an expensive operation. Of course, the actual transformation of group by key is we end up with a single key of warn together with a list of all of the dates for warnings, and the same is true for the other keys. So the end result of the group by key will look something like this. Now I want to point out that although we've ended up with, if you like, in this example, 3 partitions, there are still 3 other partitions that are now empty. And we'll see that's the case when we try this in code. So a shuffle is always an expensive operation. And as part of a training course, many of you will be looking for concrete advice that you need to follow. So I guess I could say, avoid shuffles. Well, that would be a silly piece of advice, really, because you can't avoid shuffles in really any non-trivial Spark job. If you need to do a shuffle, you need to do a shuffle. But you can think carefully about when you do a wide transformation in your job. Let me give you a simple example here. Let's say the whole purpose of this exercise was to get a report that counts the number of fatal log messages that we had over the period of this log file. Well, we could have absolutely done exactly the steps that we've just seen, and now we can simply go in, get the key of fatal, we can count the number of elements in here, and we get the answer of 2. Now obviously that's a simple example, and you can probably spot immediately that there's a major performance improvement that we could make here. We had to do all of that shuffling, and then we've actually ignored all of the warn and the errors, and we've just gone straight for the fatal. I guess it's fairly obvious in this example that it would have been much more sensible to, at the early stages of this job, because we're not interested in anything other than fatals, we could have done a filter, which you know now is a narrow transformation, and that would have ended up with an RDD that looks something like this. We've still got 6 partitions, but most of them are empty now, and we just have now a much smaller amount of data. And now at this point we can go ahead and do whatever grouping we need to do. if we do the group by key now, there's much less data to shuffle around. So an easy example here, when you get deep with your Spark and you start writing much more complex jobs, it's not always obvious that you've done a wide transformation too early. So that's a really good reason why this Spark UI is a really good guide to where you may have made some performance blunders. Now I thought it would be good to actually run through the example we've just done on the caption in the code. So this is not something that we've done previously on the course. I'll include the partition testing.java file in the practicals and code folder for this chapter. I'll also put the big log.txt file in there as well, although it is about 300 megabytes. Practicals and code is a zip file, so I think it will compress down quite well. So let's have a look at this file in detail, and it's just doing exactly what I was doing on the caption really. I'm going to add into the execution plan the loading of that text file, and then just for illustration I'm going to output the number of partitions that Spark has determined for that RDD. And I can tell you that given the size of that input file, it's actually going to split that down into 32 megabyte partitions by default, which I think is the default when we're working off a local file system. And it's fairly arbitrary, but I think, now I'm not entirely sure on this, but I think that's purely because the HDFS default for Hadoop file system is 32 megabytes. As we saw in a previous chapter though, when we ran this on Amazon Elastic MapReduce, it was a 64 megabyte partition. It doesn't really matter how big they are, it's just that they are of that kind of size. So I think we're going to end up with about 11 or 12 partitions based on the input size of that file. So now I'm going to do the map to pair, which is going to split out the log level and the date. And remember, that's a narrow transformation. There will be no shuffling. And I'm going to output how many partitions there are after that transformation. We should expect that number to be the same. There's definitely no repartitioning going on when we have done a narrow transformation. But now we get to the wide transformation, and that's where we're going to do the group by key. Notice I've not done the filter. I am going to group everything, so we should have a very expensive operation here. There's going to be a lot of shuffling to do. And then we're going to output the number of partitions after the wide transformation. Now, I will admit that for quite a long time when working with Spark, I always in my head thought, well, there's now only going to be, well, on the caption we actually had 3 partitions, but I can tell you that the file I've generated here just contains, I think it's errors and warnings. I in my head am thinking, oh, there's 2 partitions after the wide transformation. Actually, there will still be 11 or 12. The number of partitions will not have changed. It's just that most of those partitions will be empty. And then all I'm doing here in the for each is I'm looping through each key, and I'm going to output how many elements there are in the resulting value. So hope that's all very straightforward, very similar to the kinds of things we've been doing before. Now, before I run this, I've actually done it off camera, but I want to remind you that if you've got a previous run in the console, make sure you hit return and make sure that the stop button is now not lit up, otherwise you won't get the web UI. So let's give this a run, and I mean, it's not massive data, but it's going to be bigger than what we've had before. So I told you in the chapter on Amazon Elastic MapReduce what you're seeing here in the logging. So this is the number of completed tasks. So we have 11 tasks, so we can immediately see, actually, without even looking at the print line, that there were 11 partitions in the original RDD. So this is just the number of completed tasks going up and up. But for the first time now, I can draw your attention to, we have a stage 0 and a stage 1. You can probably guess now what the stages are all about. If not, I'll explain when we get to the UI. But can you see that our initial RDD partition size was indeed 11? That was just based on the size of the input file. If we double the size of the input file, we would get 22 partitions. After the narrow transformation, definitely still 11 partitions, but even after that wide transformation, we're still going to have 11 partitions, but my strong suspicion is that only 2 of those partitions had any data inside them. Well, I say it's a strong suspicion. How do we prove it? Well, let's have a look at that web UI. Alright then, back to localhost 4040, and this time it's simpler than before. We only have one completed job, and that's because we only had one action, and the action was the for each at the end. So let's drill into this, and there is so much information in this web UI. I can't show you everything, but I hope I'm going to show you all of the kind of main parts of what we're seeing here. The DAG, as we've seen previously, each of these boxes is a transformation. So we have the initial transformation here, which is the loading in of the text file. By the way, if you click on any of these boxes, it will take you to an expanded view, and very usefully it will point you back to the line of code that resulted in that transformation. I find that so useful. When you get a big graph, it can be really confusing. You see a transformation and you've no idea where it came from. Always good to map it back to the code. So line 28 of the code resulted in this transformation. Let's go back. The important thing I want to show you here is what these stages are all about. And by and large, there are some exceptions, but generally, a stage is a series of transformations that don't need a shuffle. When we get to the point where a shuffle is required, then Sparc creates a new stage. So we can immediately see at a glance here that our Sparc job needed one shuffle, because this stage here got as far as the map. Let's find out where the map came from. The map is here, line 32. This map was a narrow transformation, so it was done in the same stage as the previous. But then the next transformation was the group by key. So the shuffle, if you like, I'm kind of waving my pointer around a bit here just to say the shuffle kind of occurred here after the map. It doesn't explicitly show it, but it doesn't need to. So this is really useful, and this tells us, if we look at the stages, stage 0 here, the name of the stage, by the way, is just the name of the last transformation. And some really important information here. We can get a feel for how long it took. It was about 6 seconds, the first stage. And we had 348 megabytes of input data. That was the size of the input file. But can you see that there was a shuffle right at the end? Now, when it does a shuffle, it has to write data to disk so that it can be serialized before being transferred across the network. Now, the internal implementation of that is that data is compressed. So that's why what we're seeing here is quite a lot smaller than the input, even though we haven't removed any of that data before doing the shuffle. So we are seeing quite a significant compression of that data. And can you see that for the next stage, stage 1, the first thing it has to do for that stage is read that data back in. So that's just how it's implemented. They call it a push-pull model. Each stage will output its results and the next stage reads them back in. Okay, let's drill into the stages. So let's have a look at stage 0. And if we go further down here, there's some, well, overwhelming amounts of information, but let me point you to the highlights. We can see that there were 11 tasks, and this is very helpful really. It will tell us the average duration of each of the tasks. So I can see on average, and that's going to be the median here, on average they were taking about 2 seconds. And the minimum, the fastest of them, took about 1 second, and the slowest took about 3 seconds. Now, why is that interesting? Well, it's interesting because there doesn't seem to be a big spread across those times. Now, that makes me quite happy, and I'll explain why when we have a look at the other stage. We've also got a line covering garbage collection here. Now I doubt it will be a problem for our simple task, but if you see some big values sticking out here, then you might have a problem with creating too many objects in your tasks. And we can see that the input records were on average 32 megabytes. It looks like one of the partitions didn't quite get a complete block of 32 megabytes. Well, we can actually find that out because if we go down to the bottom, this is incredibly useful. This is a list of all of the tasks which were Java threads executed against our 11 partitions, and they were all successful. There we can see the durations, and crucially we can also see each of them were given 32 megabytes of input data, except the last one, which just kind of got a remainder there. Each of them, when it came to the shuffle, wrote about 7 megabytes of data. So that's an overview of what these metrics are telling you. Now in real life it will be up to you to work out if these values are good or bad. I reckon for this particular stage there's nothing worrying there. It's the kinds of things we would have expected to have seen. But if I go back and drill into the second stage, so this is where we're doing the group by key on line 42 of the code, line 42 here. That's our wide transformation, of course, and that's why a new stage has been triggered. Let's have a look at what we're seeing in here, and I'm a little more worried. We can see that the durations of these, remember, we still have 11 partitions, so therefore 11 tasks. The minimum time was 3 milliseconds. The median was 29, but the maximum was 9 seconds. So I have an alarm bell ringing here. There's a very wide spread of values there. And what that suggests is some of the tasks are doing nothing and some of the tasks are working really hard. So with that alarm bell ringing in my head, if we go further down and we'll have a look at the 11 tasks that have executed in this stage, we now have the answer laid out in front of us. Exactly as I described on the captions, really. It turns out that in this case, tasks ID 6 and 7 got all of the data. So we've ended up with a partition containing all of the worn keys, and we've got a second partition containing all of the error keys, and all of the other partitions are just empty. And that means that the Java code that's running on partition 6 had an awful lot of work to do, 9 seconds, and similarly for the task here, it had 9 seconds of work to do. And the other tasks were basically, I guess the 35 milliseconds is just the time it took to start up, see there was nothing to do, and then stop again. And we can also see that the shuffle readings, that's the data they've read in from the results of the previous stage, well, most of them read nothing in. So you might imagine in real life, I might have thought, oh, well, it makes sense to deploy this to a cluster with 11 worker nodes, and then we'll get really good parallel performance on the 11 partitions. That would have been fine for the first stage, but when it got to the second stage, we're going to find that most of that cluster will be sat there lying idle. So is that a problem? Well, it's hard for me to answer because it depends entirely on your real-world data set, but it's clearly something of concern that on this second stage, we're experiencing the possibility of our cluster being massively underutilized. Now, if it turns out that in the real world, stage 0 is taking 90% of the time and stage 1 is taking 10% of the time, it probably doesn't matter. 90% of the time, all 11 nodes on my cluster are busy working away. And then, okay, for the next stage, only 2 nodes in the cluster are working, but it's just a kind of a finishing off job and there's only a short amount of time spent there anyway. But if it turned out that stage 0 is only taking 10% of the time, but then for 90% of the time, most of the cluster is sitting idle, then clearly you would have a problem and you would have to do some rework. So this is definitely a problem, and I've seen this happen many, many times in Spark, where you have a job which is, I don't know, taking half an hour to run, and you need to get that job running in, say, 10 minutes. So you invest in expanding your cluster size and you end up paying for lots of very expensive instances, and you find that the performance isn't improving at all. And very likely the reason for that is you have this problem where all of your data is ending up on just a single node or just a small number of nodes because of this keying problem. In the example I've been giving, I'm sort of running out of steam with the example because I'm just counting the number of messages, which probably wouldn't be a problem because that's not going to take long to do and we're finished anyway. But we have been doing quite a lot of joins on this course, and I can tell you that joins, because joins work on keys, a join is a wide transformation. And so when you do a join, the data will be shuffled. And if you don't have a wide spread of keys, you can end up with massive joined RDDs just residing on single nodes or single partitions. And you might see out of memory exceptions, but the work that you do after the join, and that's quite typical, after doing a join you're going to be doing a lot more work, suddenly all of that work is taking forever because of exactly what we're seeing here. How do you avoid this? Well, the first suggestion is, as before, if you can possibly rework your script so that the wide transformations happen late in the process, so that your join or your group bys are only working on small subsets of the data that can be run really quickly. If that's not possible, then you might have to resort to salting your keys. Salting might sound scary, but it's quite a simple hack. It does make your script more complicated, however, so I'd only be thinking about doing this as a last resort if I really did have problems. So with the previous example, we're getting all of our warnings appearing in a single partition. So what we could have done at an earlier stage of the process is we could have changed the keys so that the key is the log level warn followed by some random number. So this random number is called the salt, and you might be familiar with salts if you've done anything with security. So in this example, it wouldn't be as neat as this, but the warn 1s are going to be in this partition, the warn 4s will be in this partition, the warn 2s, and so on, meaning that the values are now nicely spread across the entire cluster. And now after that, I can do further transformations. Now let's say, for example, I needed a count of all the warns. Well, I'd have to count the warn 1s, the warn 2s, the warn 3s, and so on, and then add those subtotals together. So it's a little bit like doing a map reduce in a way. I won't go on too long about this because for me it's a kind of a last resort. It's something I'd only do if I was really in trouble and I had no other way of getting the data spread across multiple partitions. Because it does complicate things in that at some point we've got to get this data back together again, but it does at least work. Now, my objective with showing you this was only to give you a brief flavour of salting so that you know what it is. And I think you also need to know that it's not some really big, scary, complicated process. It's a bit of a hack, really. Just to show you how this might have worked in the code. So with this code, remember, we ended up, for stage 2, we ended up with all of the data on 2 partitions, and we had 9 partitions that were absolutely unused. And therefore, if we'd used an 11-node cluster, for example, we would have 9 nodes burning up electricity and yet doing nothing. What I could have done in that scenario, as a last resort, when I did the map here, and I extracted the level, I could have just added, I'm going to add a math.random. I'm not going to do a great job of this. I'll multiply the math.random by 11 and convert that. It feels hacky, this. It is hacky. I'll convert that into an int, and that's going to be added to the string. So I'm going to get warn 0, warn 1, warn 2 in a random fashion, and therefore, and I mustn't forget to hit the enter key to end that previous job. And I'm going to run that again now. Now I think while that's running, I'll just remind you that my program is going to output the count of all of the keys. Okay, so you can see now that rather than having a single key for each level, we've got multiple keys for each level. So yeah, if I wanted to count up how many of each of these there were, I would have to work to gather together the warns and to gather together the errors. But I might be doing that after some further work that filters them down a bit or something. But all I want to show you there is, as a result of doing that, if I now look at stage 1, and you'll remember it was all very skewed, the durations had a really wide spread, but this time it's looking a lot better. The minimum was less than a second and the maximum was a second. Well, we'll look at why that's the case in a bit, but it looks like the medium of 2 seconds is actually looking pretty good. And the big difference now is for the tasks, yeah, the durations are a lot more balanced. They're not actually perfect, but certainly better than before. And you can see from the shuffle reads that all 11 partitions are reading in at least some of the data. So I definitely want to consider doing that if, after doing the group by key, I was doing lots more complicated operations where I wanted to retain the power of the parallelism. So it's difficult to explain that, and I just want to remind you that using the salting is definitely an advanced operation, only if you really need to do it, because it will cause you further headaches, but it is at least now a tool in your toolbox. So we're nearly there. We've had a look at partitions and shuffles, and what I've just been describing is an example of key skew, and that's where you have a lot of instances of one particular key and very few instances of other keys. Now, my example was just a very specific example of key skew, but I hope you get the idea. But on my list of topics was actually to avoid group by key where possible. Now, it's not really like me to say, don't use this, because, you know, you could argue that it depends on your requirements and it depends on the situation. But I've found, and I think you'll find all performance guides on Sparc all start with avoid group by key. And I don't need a new caption for this. I can pretty much use the same example as previously. So we started out with our data nicely partitioned across lots of partitions. Remember, it was chunked from the file size. But then when doing group by key, we know now a shuffle is required, which is not a good thing. We do want to avoid shuffles where possible, but really the worst thing about group by key is it is now going to have to store all of the values on a single node in your cluster. And actually this example is a perfect one. I said the input data was terabytes in size. Well, what we're going to end up with here is one of these nodes in the cluster is going to be ending up having to store at least a third of that file in memory. So, okay, we've got 11 nodes in this cluster, but after doing the group by key, we're going to have potentially a third of a terabyte because all of this data has been grouped together. So it's very easy with group by keys to end up with out of memory exceptions on your nodes, even if you have a lot of nodes in your cluster. So that's one reason for avoiding group by key. I think you'll find that group by key can always be replaced by a more performant alternative. I'm going to give you a specific example here. Let's say that our requirement with this exercise was to count the number of fatals, number of warnings, and number of errors. And it's not working because we're using group by key, and this node is crashing because it's trying to fit too many of these warning messages in memory. Now in this example, and we've seen this on the course, it would be much more efficient to do a reduce by key. Just for revision of how we did that, here's our raw pair RDD with keys and values. We would then do the trick of doing the map to pair, where we map each logging level to the number 1. Now remember, this is a narrow transformation, so no shuffling will be required at this stage. The caption doesn't capture this very well, but remember at this stage we will have terabytes of data, but it will still be spread evenly, fairly evenly, across the many nodes in our cluster. You know that the next part of this process is to do a reduce by key. We've done this many times on the course so far. Now, reduce by key will require a shuffle. So you might be thinking, well, how is this any better than group by key? But here's the big important difference with the reduce by key. Reduce by key has two phases, if you like. On the first phase, no shuffling is required, because Sparc can apply this lambda to the elements on each partition. It will apply the reduce first of all on each partition without needing to do any shuffling. So we will end up at the end of this first stage with the same number of partitions, no shuffling will have occurred, but there will be, if you like, a kind of subtotal on each partition. Because my example's not very rich here and I've only got a small number of messages here, it doesn't really come across brilliantly because you don't see a massive difference here. You'll notice on this partition, that one came from here, there were two warnings. You can just see a warn there, and that's resulted in the reduced value of warn, 2. So let me rework that and put in some more realistic values. So the reduce has been done just on a partition by partition basis. So we'll end up with partitions with a subtotal of how many messages there were just in that partition. So these are much bigger values. And that is called a map side reduce. I'm not sure why they call it a map side reduce. I think I'd rather call it a partition side reduce. But the point of all of that is, I mean, we're not at the final answer yet. It's got to gather together the fatals, for example, from each partition onto a single partition. Therefore, it has to do a shuffle now. But I hope you can see that the amount of data it's shuffling is dramatically reduced. In each partition, there's going to be at most one entry for each key in our key space. For us, that's going to be just 4 or 5. So the shuffling is really minimal. So we end up now, after the shuffle, with all the fatals on one partition, the warns on another, the errors on another. So of course, all it now needs to do is apply the reduce again on these subtotals to get the final results as seen here. So just to reiterate then, reduce by key will do a reduce on each partition first, that's your map side reduce, and that will greatly reduce the amount of data shuffled around. So you're going to find that group by key in most circumstances can be replaced with an operation such as reduce by key. If you've got a richer requirement, then there are other transformations available in the API, which we don't have enough time to go into details of all those transformations, but I hope you get the feel for what I'm getting at. Group by key is generally to be avoided. Just one last topic to cover then, and that's caching and persistence, which I know it sounds big and scary, but I hope I'll be able to demonstrate this with a simple example. If we go back to our partition testing, I'm just using this because it's simple. I'll just remember to hit return to terminate the previous program. And let's rework this. So on line 34, we don't have that salting anymore. We would avoid salting unless absolutely necessary in real life. So we're back to the state now where we're running through our transformations and then we're counting how many elements there are for each key. But let's say we also want to get the grand total. What was the total count of all of the elements? Well, a really simple way of doing that would be to take our RDD, which is called results. We can call count on that RDD, and we can pass that into system.out.println. I hope you'll agree, nothing scary or confusing there. But I have actually made quite a serious performance blunder there. It's quite subtle, and I don't know if you've spotted it, but I certainly could not spot that when I first started working with Sparc. Let's run the program and we'll have a look at the web UI. I wonder if you expected that output. So we had the two stages as usual, and it output the elements for the keys, which is what we wanted. But then when we call count, it ran another stage, which seems to suggest that to do the count, it had to do a shuffle. Really? Why would it have to do a shuffle? And so this time if we go to the jobs page, and what we're seeing here is a list of all of the actions that were performed. We only had one entry in here before, and that was the for each, but we now have a separate entry for the count. So I think we'll find if we look at the for each, nothing will have changed in there. This is exactly the same as before. But if I go into the count, you might be surprised to see this is the stage 3, the extra stage that we didn't expect. It has done the group by key again. And it's also got a stage 2 here, which it's skipped. That's confusing. I'll come back to explain what that's all about, but the first thing to address is, why is it running another stage just to get that count? It appears to be redoing previous steps that were already done. If I go back to the first job, it already did this group by key and map values in stage 1. Clearly there's something worrying here. And again, it's all back to the fact that when we have a Java RDD here, we don't really have any data at all. There is no data loaded in by this line. What we're doing is we're saying we need to add an element to the execution plan. Now it's only when it reaches an action, such as the for each, this is the first action, and therefore that will become a job, and it executes the plan required to achieve these results. So it's going to do the transformations, it's going to do the shuffling, it's going to do the grouping, and then it will output the results. But once it's output the results, the real RDD in memory, the actual data, will be discarded. So when it comes to the count, believe it or not, it has to go all the way back, in this case all the way back to line 28, to execute all of these steps again, which is a real surprise to anybody starting with Sparc. And it's the one big secret that I've been keeping all the way through this course. And, you know, I feel a little bit bad about that, but I hope you understand that you really need to have done quite a bit of work with Sparc before you can address this concept. So when you get to an action, it has to go all the way back to the initial RDD to rerun. It's not storing all of this intermediate data in memory. Now there is one optimization. If I go back and look at, this is the counts job, that's the second job that was carried out. And as I said, it's had to go all the way back to the beginning to where it loaded in the text file, and it's had to run all of those stages again. Well, you can see it hasn't. It's actually skipped stage 2. Now this is a performance optimization that was added, I think, back in something like Sparc 1.3. And it's simply that whenever a shuffle happens, so we know a shuffles happen here at the end of this stage, or I should say actually, if I go back to the first job, when the shuffle happened here at the end of stage 0, the results of the shuffle are written to disk. I briefly mentioned that before, as a result of this shuffle write. And that means when it came to do the second job, I hope you're clear now, it may be surprising, but it has to go all the way back to the beginning. But it's able to optimize because it knows it's already done this and already written the results to disk. So that stage can be skipped, and stage 3 can simply read that shuffle data back into memory. So it's not quite true that it always has to go all the way back to the start. In fact, for an action to occur, it's going to have to go back to the last shuffle stage, basically. So in this example, to do the count, it's had to do the group by key again. By the way, I didn't mention this map values, we don't have a map in our code, but it's actually just part of the group by key process. It's sort of an internal implementation detail, and we can tell that if we follow the link there, you'll see that they both map to the same line of our code. Line 42 is indeed the group by key. So the point of that is it's had to do the group by key again when we've already done the group by key. So this may seem really inefficient, that every time an action is performed, Sparc is, if you like, going all the way back to the beginning. Actually not the beginning, but it will be all the way back to the results of the previous shuffling. And it's very easy to end up with the situation where you're doing a lot more work than you think you're doing in your script. Now what we can do to avoid this inefficiency is with any RDD, we can tell Sparc that we want to store that RDD in memory and keep it there for future operations. So in our example, when we did this group by key, we could have, before we perform the actions, we could have said that the results, again, it's another operation on the RDD, and it's simply called cache. Pretty easy. And remember, it's a method that returns an object, so you need to reassign it. And that's just telling Sparc that the actual data that's going to be resulting from this transformation here, it needs to, I think of it as a checkpoint. It needs to store that data physically in memory. And that will mean in this specific example, when it comes to the for each, it will be working from that cached data. And similarly, when we get to the count, it will work from this cached data as well. In other words, it won't have to run the group by key again. So let's see the results of that. Again, I'll need to remember to stop that program and run again. Well, actually I didn't feel a difference there, and the reason is, I don't know if you can see this warning here, it is warning me that there was not enough space to cache that RDD in memory. But yeah, unfortunately cache will only work if there's enough space in RAM. Now what will happen if cache fails is it will just give you this warning and then it will carry on as before. So unfortunately this stage 3 did have to run that group by key again, and I definitely felt the performance impact of that. So cache is okay if you've got relatively small RDDs. The other alternative instead of cache is to use persist. Now persist takes a parameter of type storage level. And there's a set of values you can use there, and they're not very readable, and I'm afraid there's no good API in the Java docs for this. But we have basically the option of disk only, memory and disk, or memory only. Now if you go for memory only, you're going to get exactly the same as cache. They are the same operation. But if we go for, I think in our case, if we go for memory and disk, it will try to use memory if possible, but if there's not enough space in memory, it will fall back to writing that RDD to disk. So we can try that. Again, I'll need to hit return to terminate the program, and let's run again. Okay, so the warnings are now telling us that there wasn't enough space to cache it, but instead it's persisted to disk. Now I have to admit that in this run I didn't feel a performance improvement from this, and my guess is, I really don't have time to analyse this any further because I've got to release this course, but my guess is the overhead of writing it to disk is actually not saving me any time on this specific example. But if you were working with much bigger data sets with a much bigger cluster, then this could well make a big difference. Back on the Sparc UI, again we've got two jobs, one for each of the actions. Now this time if we look at the first job, the for each, the difference is when we get to the map values stage, the green circle denotes that this RDD at this stage was cached. And now if we look in job 1, now you might not expect this. I expected not to see a stage 3 appearing here on the graph. I think it's slightly confusing UI. It is appearing on the graph, but the fact that there's a green circle there is telling us actually this RDD is being read from the cache. So this group by key step wouldn't have needed to take place. And that's why, although there was a stage 3, the green circle is telling us that it's worked from the cached value. Now this has just been a small example just to give us a feel for the web UI, but what I'd like to do to complete this chapter is to go back to our viewing figures example, which was a far more significant exercise. And I don't know if you did that exercise, but yeah, we had quite a complicated set of transformations. So I'm planning to do the same thing here. Before I close the Spark context, I'm going to do the trick of doing the scanner and a scanner.nextLine, and I'll make sure that in the console, yeah, I've terminated the previous run. I'm going to run this viewing figures example now, and we'll have a quick look at how this looks in the Spark console. And yes, significantly more complicated. We've got several stages, a 0, a 1, a 3, and a stage 6. But can you tell from this logging, it's trying to express that stage 6 here has been run in parallel with stage 1. Now that's interesting. We haven't seen that happen so far. And that's what Spark's going to do. If it determines that on a particular pipeline of transformations, one stage isn't dependent upon the output of another stage, then it can run them in parallel. So that's really the point of this DAG, this execution plan, and one of the main reasons why it runs it lazily, so that it can spot optimizations like this. But let's have a look at it on localhost 4040. Now we're seeing two jobs again for the same reason that we saw two jobs earlier. When we're doing a sort by key, it will trigger off a job to do the sorting. So we're seeing a separate step for the sorting and a separate step for the collecting. Now, I won't get hung up on that just now, but I think if we follow the link to sort by key, that's going to give us actually quite a scary visualization of the DAG. Certainly far more complicated than anything else we've seen so far. Now this video is getting long, so I won't go too deep into it, but you should be able to piece together what's happening based on what we've learnt so far. It's only a bit more complicated, this DAG, because we are working on that exercise. We did work with 3 different input files. So the stage 0 here, if I follow the link, is pointing to line 103, and it's actually reading in the titles of the courses. Whereas this stage here is reading in the viewing figures, and this stage here is reading in the chapter data. And then, well, I can't get my head around of what we did after that. It's quite complicated, but we have various jobs where we're doing things like joins, for example. If we take this stage 4 as a working example, this was on line 47. On line 47, we were joining together the viewing figures and the chapter data. So going back, clearly this stage 4 depends on, just following these lines back, it depends on these 2 sets of input data, this one here and this one here, being present. And actually this input data here was the viewing figures, and you might remember we had to remove the duplicated views, which is the reason for this intermediate stage here. It all hangs together, but I've realized just scanning through this that there's something very odd going on here. We only had 3 input text files. We have a stage reading them in, but if we go all the way over to stage 6 here, You can see we're reading one of the files in again. What's going on there? Well, let's follow the link. This is the chapters data. That's really odd because if I go to stage 2, we've already read that file in stage 2. Now, I admit this is complicated and you might want to stop the video and have a good look at this for yourself and have a deep, hard think about what's going on. But again, it's all to do with the lazy evaluation and the fact that when you do a transform, the input data for the transform is not stored in memory unless you ask otherwise. Now, what's going on here is, let's have a look at this map. So this is the first transformation that we apply to that text file. So that map is happening on line 134. So actually that map is right down here, and it's just the splitting of the data into a pair RDD. And then the results of that are passed into this join in stage 4. So it's being joined, and it looks like if I follow this line through, it's being joined to those distinct viewing figures. So the data inside the chapters file is clearly needed so that it can do this join. But then much later on in the process, and yeah, it is complicated this, we have a reduce by key operation here. And it's here on line 39. And this is where we worked out how many chapters there were for each course. And I did that as a warm-up exercise, but the data's needed later on. So my point is, we're reading the chapter data RDD here, but we're also doing a transformation on the chapter data RDD here. And as you know now, the data in these RDDs is not by default automatically cached unless you force Sparc to do so. To put that another way, when it had to do the join here, it clearly needed to load the data in from the chapters file. But then in a different part of the process, we needed that data again. That's the point of this. We've used this input data in 2 separate places in our script. Now, I wouldn't have spotted that without looking at this graph and spending quite some time trying to work out what's going on. So I'm guessing you might be confused at this point. Let me just reiterate. What we've identified is that the data in this text file is used in 2 separate places in the process. And you know from what we learned previously that Sparc's going to have to recalculate that data each time it's used. You know the solution to this now? We could be taking, if I hover over here, this mapping operation that's done here on line 134 is the same in stage 2 and is the same in stage 6. And therefore, we really should be caching the results of that mapping operation. So if we look on line 134 of the Java, and that's here where we've done this map to pair. Now we're returning a Java pair RDD here, so I think what we can do quite simply on the end of here is simply Fluently add in a cache. So now this data, when it's read in, will be stored in memory. And I think we'll have room in memory for this, and that will be reused wherever it's referenced later on in the graph. So quite an advanced example that. I'll just terminate the previous run and let's see the difference. Now I have benchmarked this off camera, and because we're working on such a small set of data, I'm not really seeing a big difference. And actually, thinking about it, the chapters.csv file, I don't know if you remember, it's actually quite small data. So in practice, for this example, I don't think we really need that cache. I think we can easily take the hits of sort of laboriously loading in that data twice. It wouldn't be a big deal. But in real life, if you had done further operations, further transformations on this RDD, you might have done another 15 transformations on it before you then go on to use it. Well, you'd be doing those 15 operations more than once, and that would be obviously quite wasteful. So that's where the cache would become useful. Anyway, I just want to show you the difference now. In fact, I'll just refresh that page. And now the difference is you can see that green circle highlighting that these 2 points in the graph are working from the same data. Now, I realised that was quite advanced, but I didn't want to just work with simple examples. I wanted to get a little bit more complicated so you can see the kinds of problems you're going to face when working with Spark in real life. Hopefully in this chapter I've given you a good look under the hood, and I could have spent an entire course, I could have probably spent a series of courses looking at the internal workings of Spark, but I think that's probably enough if you're wanting to get started with Spark, and certainly if you're a Spark programmer. I hope you've now got a feel for some of the traps that could catch you out when working in Spark. Thanks for watching the course. I'll see you hopefully in the next module where we'll be looking at Spark SQL or Spark SQL. In the meantime, happy sparking.